So as we go through this one, guys, there's not going to be a lot for you to write down, at least not at first, okay? Because the first part of this is just talking about balancing chemical reactions, which you guys already know how to do. This is just kind of so that you have it in your notes. It's in the notes package, so again, it's not going to mean you need to copy down a lot of stuff here, okay? So the key points are, we need to understand that the amount of atoms on the reactant side of an equation must be the same as on the product side. That's why we balance chemical reactions. Okay? Learn to use coefficients to balance equations. You already know how to do that. Okay? And understand that matter cannot be created or destroyed. That's, of course, why we balance chemical reactions, to obey that primary law, okay, of the law of conservation of matter. So the law of conservation of mass says that mass must always be conserved in reactions because matter cannot be created or destroyed. Since all matter has mass, the mass of the reactants must equal the mass of the products. Early on in chemistry, this was something that people had difficulty proving. Because if a reaction produced a gas, the gas would escape. Gases have mass, and then suddenly the products were lighter than the reactants, and it was hard to explain why. Okay? It wasn't until people started being able to, or started to realize that gases have mass, okay? And they don't just, when they float away, you lose that, and they have to be captured. Right? So if you capture the gas, okay, you'll find that, yes, in fact, the products and the reactants have the same mass. Right? If you ever doubt that gases don't have mass, okay, pick up a tire that's flat, like one that's on a rim but's flat, then inflate it and pick it up. Okay? You put enough gas in that tire, it'll change the mass of that tire significantly. It'll weigh a lot more and be a lot heavier when it's actually full, because it's compressed air. And you put a good volume of air in the tire when you fill it. Okay? And you won't notice it with a balloon. People are like, what if I just do it with a balloon? If you had a really sensitive scale, put the balloon on the scale, then blow it up, put the balloon back on the scale, and it'll be a little bit heavier. Doesn't involve you having to get all dirty by picking up wheels and tires. And you have to have a pretty sensitive scale for it. All right, questions so far? Okay, so the law of conservation of mass says that in any physical or chemical change, the total mass of the starting materials must equal the total mass of the product materials. This is why we balance reactions. Which one of these three on the bottom is showing us obeying the law of conservation of mass? D, yeah, definitely D, right? I mean, we can tell right here that there aren't nearly enough yellow atoms in B. There's way more yellow atoms in A than there is in B, okay? In C, there's just not enough of anything, okay? There's way less dots, period, okay? And in D, right, we got 2, 4, 6, 8, 10 of the red ones, 2, 4, 6, 8, 10 of the red ones, and we've got 3, 6, 8 of the yellow ones, so there's 3, 6, 8 of the yellow ones. Right. Is it okay that some of the yellow ones didn't react? Yes. Most of the time in a chemical reaction, you have what's called an excess. That is, you have a little bit more of reactant A than you have of reactant B, and so as a result, there's some left over at the end. Okay? There's almost no way to make sure that you get exactly the right amount of both so that it all completely reacts and nobody's left at the end without somebody. Okay? There's always going to be a little bit left over. All right, so for balancing a chemical reaction, and again, this is not something you have to write down because you already know how to do this. It's just so you have it in your notes. Okay? Write the chemical formula for each reactant and product. You don't have to have the state of matter. Okay? Try balancing the atom or ion present in the greatest number. Right? We talked about how that's the best thing to do for all reactions except combustion, right, which has its own set of balancing rules. Okay, so use coefficients, that's the big numbers in front of the element or compound, to get equal numbers of atoms on both sides. Okay, step 3, repeat step 2, okay, to balance each of the remaining atoms and ions. Check the final reaction equation to ensure, okay, that all of the atoms and ions are balanced. So that's the stuff we've been doing all along. Okay, we're familiar with how to do that. All right, this is just an example of it. We actually did this reaction last week. Okay, got 4 reactions here on the board. Quick review. if I want to predict the products of a chemical reaction, the first step is I need to identify what type of reaction is happening. Once I know what type of reaction is happening, I know what pattern to follow, I can figure out what's on the product side. On the product side, I need to drop and swap ionic compounds and check for special elements. And then I need to balance my final equation. Right? That's all there is to this. So let's do number one together just as a quick review. So question number one, I've got calcium reacting with oxygen. What kind of reaction is that? That's a synthesis reaction. In a synthesis reaction, the two elements that are reacting combine to form a single compound. How did I know to write the calcium first? Yeah, it's a metal. Metals always get listed first, and it was making an ionic compound. Since it's an ionic compound, I need to drop and swap it. Oxygen's a -2, calcium's a +2, so this compound is fine the way I have it written. Now what? What's left to do? Balance the reaction. All right. Largest number is on oxygen. There are 2 oxygen on the reactant side, but there's how many over here? Just 1. All right, so I can just do that? No. Okay, I can't put in the little numbers. Those come from my drops and swaps, and I already did that. All I can do is put in coefficients. When I put that 2 there, it balances my oxygens, but it also makes 2 calciums, so what needs to go here? Right. Is my equation balanced now? It is. Okay, try the other 3. Give you a few minutes and then we'll go through them together. It's okay to have your notes out on the types of reactions if you want them out. Okay. So for number 2, I've got only one reactant, magnesium sulfide. What kind of reaction starts with only one reactant? Decomposition. All right, so in a decomposition reaction, the compound simply breaks up into its 2 component elements. Those component elements are magnesium and sulfur. Now, I don't have any ionic compounds to drop and swap, but what do I have? I have a special element. The most special of all the elements, sulfur, which comes as an 8 when it's by itself. So always have your periodic table out when you're doing this. Have a look for those colors, right? If you're using one of those colored elements and it ends up by itself, okay, you need to put the correct number on it. Now that I've done that, now I can balance. Obviously, I want to start with this number as it's the only thing that's out of balance. So there are 8 sulfur over there, so I need to put an 8 here. That gives me 8 magnesiums and 8 there, and now everything is balanced. How many people have done the third one? Okay, so the third. What kind of reaction is number 3? It's a combustion reaction. What are always the products of a combustion reaction? Right. Carbon dioxide and water are always our products. So there's no figuring to do here. That's just something you have to memorize. Okay. There are 2 rules for balancing a combustion reaction. Balance it alphabetically and the rule of 2. Do I need both? When do I apply the rule of 2?
When the seed has an even number?
Right, when there's an even number of carbons. All right, this is not an even number, so I can go straight to it. There are 3 carbons here, balancing alphabetically. Now there are 3 there. There are 8 hydrogens on the reactant side. 4 times 2 is 8 on the product side. And now I can do the oxygens. There are 6 oxygens here, 3 times 2 is 6. And there are 4 more here for a total of 10. 5 times 2 is 10. Okay. How many people have done the last one? Okay. What kind of reaction is the last one? Double replacement. It's 2 ionic compounds. All right. When we have 2 ionic compounds, all we do is swap the metals. So that means that hydrogen will end up with hydroxide, and sodium will end up with chlorine. All right, did I just make 2 ionic compounds? What should I check? What do we do with all ionic compounds when we write their formulas? Drop and swap. They're both good, okay? This is a +1, this is a -1, this is a +1, this is a -1, so they're all good, okay? And is it balanced? It is. Everything's a 1, right? There's no little numbers. Everything's a 1, and it's already balanced, so that was an easy one. Okay. All right. Is this ringing a bell? I know you had a week off since we last talked about predicting, but it seems like you guys did okay there. Okay. Let's take about a 5-minute break here, and then I'm going to put some ones that I want you to try up on the board, and some tricky balancing ones. I know. Sure. Yes, you can. All right, guys, let's look at the first two here. So for number 5, what kind of reaction are we looking at there? It's a synthesis reaction, right? There's two elements reacting. Okay, they are going to react, and they're going to form a single compound. That compound will be beryllium iodide. Okay, it's an ionic compound, so I've got to drop and swap it. Iodine's a -1, beryllium's a +2, so I'll get BeI2 as my formula for that. And then I need to balance it, so I'm done, because it's already balanced. All right, what kind of reaction is number 6? The single replacement. I've got an element reacting with an ionic compound. Now, single replacement are probably the most difficult ones to do, because they have the most to think about. The element, whatever it is going to replace the part of the ionic compound that it's like. Potassium, metal or non-metal? It's a metal. So it's got to replace the metal, which in this case is iron. Right? So it's going to swap out for iron. That means that potassium will end up with oxygen, and iron winds up by itself. Okay. Now, did I make an ionic compound? What do I have to do with it? Drop and swap. Okay, so oxygen is always a -2, potassium is always a +1, so I got K2O, right? And I got iron. Is iron special? It is not. Okay, it's a metal. There aren't any special metals other than hydrogen. Okay, so that's good there. Now I just need to balance the whole reaction. Right now, the only thing out of balance is potassium, so that'll be an easy balance. 2 there takes care of everything. Okay. How many people have done number 7? Okay, I'll give you guys a few more minutes and we'll do 7 and 8. So for number 7 here, I've got copper 2 sulfate reacting with magnesium chloride. What kind of reaction is that going to be? They're both ionic compounds, so it's double replacement. Okay, in a double replacement, we've said all we do is swap the metals. So that means that copper will end up with chlorine, and magnesium will end up with sulfate. Okay, I just made 2 ionic compounds. What do I need to do with them? Drop and swap. All right, so copper can be a 1 or a 2. What was it over here? Sulfate's a -2. So this was copper 2. Okay, that's going to happen in both types of replacement reactions. If you get a multivalent metal, you've got to look at the reactant side to figure out which charge it is, because that's going to be important when you drop and swap it on the product side. It's not going to change. Whatever it is on the reactant side, that's what it is on the product side. You don't change types, okay, from one side of the reaction to the other. So this is a 2+, this is a 1-. So we got CuCl2, magnesium's a +2, sulfate's a 2-, so that compound's fine the way it's written. All right, now I've got to balance this whole reaction. Done. Okay, the only thing that's not a 1 is chlorine, and it's a 2 on both sides, so we're good there. Okay, everybody with me on that? So that one has that little trick. It's one of the things we have to watch out for, and it's going to happen in the replacement reactions. Okay? It can also happen in a synthesis reaction. Right? In fact, let's maybe just quickly talk about that. If I have this synthesis reaction, okay, I have iron as an element, which has no charge, reacting with chlorine other side, I make an ionic compound. But iron has more than one possible charge. How do I figure out which one it is? Well, I can't drop and swap because to drop and swap, I need to know what charge iron is. And there's no way for me to find that out over here. It isn't with anything. So, this is what you do. You look at your periodic table. Whichever charge is listed first is the most common charge. That's the one you use. If there's no way to figure it out, as in this situation, and only this situation, then this is the only time this will come up, okay? You use the most common charge, right? So for iron, that's 2 or 3? 3? Okay, so then we say 3 plus, 1 minus, FeCl3, okay? That's the only situation in which that'll come up. That's how we do it. Eric, question? You can. All right. Number 8. What kind of reaction are we looking at there? Combustion reaction. Okay, combustion reactions always produce carbon dioxide and water. Do I need both balancing rules for this one? I do, yeah. 4 is an even number. So I'm going to apply the rule of 2, and then I'm going to start balancing. 2 times 4 is 8. So we got an 8 there. 2 times 10 is 20. 10 times 2 is 20. And now I can do the oxygens. 8 times 2 is 16 oxygens here in the carbon dioxide, plus 10 more for a total of 26. 13 times 2 is 26. Okay. Questions on that one? Now for number 9, okay, we've got rubidium with phosphide. So this is rubidium phosphide. It's the only reactant. So what kind of reaction am I looking at there? Is it decomp, right? Okay, so it's a decomposition reaction. Okay, so I got Rb, and then I've got phosphorus. One of the things I always need to watch for in a decomposition reaction is the production of special elements. Do I have any? Yep. Phosphorus needs to be a 4. Is rubidium special? It's not. Okay, so now I've got a balance. Biggest number is 4, so I'm going to start with that. 4 phosphorus on that side. Now there are 4 phosphorus on this side. How many rubidium do I have? 12. 4 times 3 is 12. So I just got to put a 12 there. Okay? Sometimes that happens. You've got to put a really big number in front of something. And then our last one. We've got lead 4 chloride reacting with cobalt 2 phosphate. Okay? So, what kind of reaction am I looking at? David, what kind of reaction is this? Double replacement, right. Okay, so I've got to swap my metals here. Okay, so I'm going to have lead is going to end up with phosphate, and cobalt is going to end up with chlorine. All right, I just made 2 ionic compounds, and both of them have multivalent metals. So I've got to figure out the charge on both of those metals before I can drop and swap those 2 ionic compounds. All right, so figure out which charge is on lead. I look to my non-metal. Chlorine's a -1. Okay, there's 4 chlorines, so that means this must be lead 4. All right, so now I can go back over to here and go 4 plus. Phosphate is a 3 minus. Okay, when I drop and swap, I'm going to need brackets. I'm going to need a 4 outside the brackets. I'm going to need a 3 here. Crazy. Big numbers. Okay, and then I've got to do the same thing with cobalt. Phosphate is always a -3. 3 times -2 is -6. So that means I've got to get 6 positives from 3 cobalts. That makes this the cobalt with the 2 plus charge. 2 plus, 1 minus, COCl2. All right, what's my biggest number? Sorry, did everyone follow what I did with those multivalent metals? Okay, no different than when we're figuring out which Roman numeral to put in the name. It's the same process. I just have to recognize that if I'm predicting the products of a reaction and I've got multivalent metals, I need to know which charge they are. Okay? So I can drop and swap on the product side. That's a very common thing for people to forget. Okay? All right, my biggest number is 4, and it's phosphate or chlorine. Phosphate's got a greater charge, so I'm going to start with it. Okay, there's 4 phosphates over there, but there's only 2 here. So what needs to go here? Okay, so I put a 2 here. That's going to give me 6 cobalts. So I'm going to go back over here and make sure I've got 6 cobalts. That gives me 12 chlorines. Back over here. What needs to go in front of this to make 12? 3, which works out perfectly because there's 3 leads on the other side. And now balance. That would be as hard as they would get. That's got a little of everything in it. So some multivalent metals, tricky balancing, brackets, all of it. All right. So far, I've only asked you to predict chemical reactions that were written in formula form. What if I give you the reactants in words? Does it change what we do? Does it increase the possibility of error? Yes. Okay? If you don't have the reactants written out for you, and you've got to write them out, it's just one more place where you could possibly forget to do something. Okay? So, don't forget to do something. You know how to write the formulas for chemical compounds. Follow the rules. Okay? We know that for ionic compounds, we write the charges, we drop and swap. For molecular compounds, we use the prefixes to figure out what there is. And, the thing most people forget, special elements. Okay? If I was to, for example, say, in this one, write it out in words, it would just be beryllium plus iodine. You'd be surprised how many people would write that like this. How much of that are they going to get right? Nothing. Okay? They're not going to get any of it right. Okay? Well, I shouldn't say that. They might get the products right. They might get BEI2 when they drop and swap. Problem is they won't be able to balance the reaction correctly because they'll put a big 2 in front of this one. There shouldn't be anything in front of it. Okay? So little things like that are a little bit trickier because it's easier to forget them when they're not written out for us. So they're little things to watch for. Okay, so this sheet is in your digital workbook. Okay, now the balancing that's up top here, we'll get to ones this tricky. So if you want to try them, go for it. We will get to ones like this. They're going to be a bit humbling. I wouldn't try them just yet. Okay, I'd wait till you get a little more practice with this stuff, then go back. You start to get cocky, go back and do these ones. Okay, they'll make you feel humble again. Okay, so I want you guys to try these ones. Now, one tip that I'm going to give you. Anytime you have water as a reactant, I would write it like this. Okay, because it's probably in a replacement reaction, and it needs to be like, it needs to go as hydrogen and hydroxide. It wouldn't be wrong to write it like this. It's just you're going to predict the reaction differently if you write it like that. Okay, so let's do number 1 as an example here. Okay, so on number 1, I've got potassium is added to water. So if I write that the way I originally told you, it's going to look like this. Whoops, that's not the way I originally told you. This is the way I originally told you. Okay, what kind of reaction is that? It's a single replacement reaction. Okay, so in a single replacement reaction, potassium is a metal, it'll replace the hydrogen, and I'll be left with this. I've got H2 and potassium hydroxide. That's what happens in that reaction. Okay? You get a highly basic solution and hydrogen gas. Okay? This also usually, if you guys ever seen when someone throws sodium into water and it explodes? Okay? This is a very similar reaction. Now, the other way we could have written this is we could have written it like this. K plus H2O. Now, if I predict the products of that reaction, do they look like the products of the first one? Or will I get a different set of products? Okay, well, if I look at this and I've got H and O, I know this is my metal, so I'd swap it out. Okay, and I'll end up with this. H2 plus K with O, this is a -2, this is a +1, K2O. And then I need to put a 2 here. Those are two very different reactions, aren't they? And they both be right. Okay, if I don't, there's no right or wrong on that. You wrote water one way, you wrote it the other way, and you predicted the products of the reaction, both of those answers would be correct. Okay? I would recommend whenever water is a reactant, you write it as HOH. That's the way it most commonly goes in replacement reactions. Okay? But if you wrote it the other way, and you got that as your answer, it would also be correct. All right, so on that note, you can look at number 2, which has exactly the same issue. So I'd write it as HOH. Okay, give you a chance to get ahead of me there, and then we'll look at doing a few of them together. Okay, remember, these are a little bit trickier because we got to be mindful of, we got it in words, so we've got to make sure we get our reactants written correctly before we move on to the products. So for number 2, we said water is a reactant. We should write it as OH, capital O. Right, making this a single replacement reaction where calcium is a metal and we'll be replacing hydrogen, the metal in water, giving us hydrogen. How do I know to write it as H2?
Because there's 2 hydrogens on the left.
Nope. It's a special element, right? It's listed in the top right corner of my periodic table. Okay, it's one of the special elements. Okay, and I would write this CaOH. This is a +2. This is a -1. So I got to put brackets around this and put a 2 there. Okay. So in regards to that, there are 2 on the right. Well, actually, there aren't 2 on the right. There's 1 OH and 1 hydrogen. So now when I balance, putting a 2 here makes sure I've got 2 hydrogens and 2 hydroxides, which is what I have on the other side. And now my equation is balanced. Everybody all right with that? Okay, what's the trick in the next one? It says I have magnesium solid, which is just this, and nitrogen gas. What does that look like? N2. That's one of those ones I got to remember. If I'm putting elements in, I need to check to see if they're special or not. Magnesium's not, nitrogen is. Right? That's going to be a synthesis reaction where magnesium and nitrogen go together. That's an ionic compound. Okay, this is a -3. This is a +2. Drop and swap. Okay, what do we do next? Juliana, what's next to do? What do I have here? Right, so what needs to go here? Big 3. All right, now it's balanced. Now I'm good. All right, keep going there, guys. Okay, so tomorrow we'll be working on, I think I have the computers protected, so we'll be working on a research project for the senior, I think. If not, we'll be doing more of this, and you have a quiz tomorrow. It will have all reactions stuff on, okay? Some of it will be just reactions like we did before the break, and there might be like a predicting one at the end. So I'll post the practice quiz at the end of the day as well. All right, good work today, guys. All right, have a good rest of your first day back.